Thank you, everyone. Sorry by advance for the people that was looking for the iOS like talk. I mean, I will be your replacement, but I hope you will learn a lot of stuff. Basically, the really good part is that I think my talk will just follow what basically Mark told you during the keynote, like about the step of being like a researcher and testing stuff and so on, because that's basically what I've done on the past 2 years with this project. Was basically I was kind of a bit new about like the blockchain node and especially Ethereum and what was supposedly like the evolution that will happen. And you will see that it's basically a talk focus on the fuzzing journey and the different steps I made to reach a certain goal, that was finding vulnerability and so on. I will not talk too much about the vulnerabilities themselves because, I mean, I suppose not a lot of you are on the blockchain security ecosystem, so it will not make sense, but at least you will be able to reuse, like, I hope, a bunch of like tips and tricks regarding dealing with huge projects, and especially with projects and that are not really common, and dealing with a bunch of characteristics that are really special. So just to tell you a bit more about me, I'm Patrick. I'm running the Fuzzing Labs company, where basically I'm doing training about fuzzing and on a bunch of stuff, mainly like Rust, Go, WebAssembly, browser, and so on, and a lot of blockchain stuff, of course. I'm French, you can hear that, of course, and I'm also running the Fuzzing Labs channel. So where basically I'm doing like fuzzing every week, and there is one video per week. So first of all, I will need to tell you a bit more about what is Ethereum 2.0 and also what is Ethereum for the ones that are not aware, of course. So basically, Ethereum, I consider it's like one of the first blockchains that I think it was even the first one, to run smart contracts. So of course, really famous blockchain with the crypto pump and so on. It's basically in terms of, if I need to synthesize with like what is under the hood, it's just a peer-to-peer network where basically you have multiple nodes that will discuss to each other. The way they will discuss, so it's using P2P stuff, and they will basically send block and transaction, and it's basically they are sharing the database together, and yeah, that's basically pretty much all. So that's mostly one. So that's the idea. So the first thing we can say is, of course, there is a lot of stuff to do with the networking stack, especially if you are thinking that all those nodes will basically communicate to each other. So the main kind of attack we can have in such case is basically another miner that will attack you to maybe do denial of service or this kind of vulnerability. So it will be basically using the ENR and all this other networking stack. And then we have the beacon chain itself, so the different basic blocks that are sent to each other. And those ones are basically serialized and encoded into what we call SSZ. So it's specific format, and it's more easy to just give them and share this kind of stuff. And basically this object will contain the block, the transition, and all this kind of blockchain-specific stuff. So in terms of bugs that are really interesting, we have all the stuff that will crash or panic, because, as I mentioned, that means a complete denial of service of the node, so that's really bad. Of course, we are looking for memory corruption, and if we can get RCE, that's even better, but you will see that because of the language they actually choose, it's not something that we will see really often, to be honest. And one kind of bug that is really specific to blockchain are consensus bugs. So that means it's a logic bug, but since we are dealing with blockchain, if we have a logic bug, that means you will get part of the network that will do one thing, the other part will do another thing, and that's what we call a fork. So if we have something like that, it's really, again, one of the most critical vulnerability. You maybe heard of some of them recently on other blockchain. And that's the kind of bug that leads to the development of this further that I'm gonna discuss. So the target of today will be those one. So the first one is Lighthouse, developed by Sigma Prime and in Rust. The other one, Prism in Go, Nimbus in Nim. So maybe some of you don't know what is it, and that's perfectly normal. You have Teku in Java, and you have, so I put this one as a client. It's a client and not really a client. I mean, it's written in JavaScript and TypeScript, so you can think that it's going to be maybe complicated to have like some proper node and proper software at the end that will just run everything in this language. So the main idea is Lodestar is also providing a lot of library for web application and so on related to Ethereum. So that's still a really good target for us. And especially because, if you remember, they should all follow the same specification. So that's already a really good point. So at this point, the main difficulty, as you can see, is we have, let's say, 5 different software written by 5 different teams in 5 different languages, and they should basically follow the same specification. So what can go wrong? So let's talk about Beaconfuzz. So that's the further I basically wrote, and I wrote it with Sigma Prime, another company that specializes in blockchain security, and also one of the developers of one of these clients. So basically, to give you a bit of history, the project starts not with me, but with Guido, that is really well known with the, I think it's Crypto-Fuzz project, and basically he's doing a lot of differential fuzzing and so on. So basically he created a proof of concept using Leap Fuzzer written in C++, and he was already starting to do the job in 2019. So after that, Sigma Prime gets the lead on that, and they receive a grant by the Ethereum Foundation to basically continue the project and find some new bugs. And after some time, I discussed with the Sigma Prime guy, and we find out that it could be a good fit to work together. So that's the start of the Beaconfuzz project. So as I mentioned, I'm going to discuss about like basically the complete process that we have been through. So the first thing I take a look was basically the existing code, and it's in C++, and I really don't like C++, so that was the main issue for me at first, because I mean, if I need to spend like 1 year and more on a project, and I don't like the language, and I'm really not happy to write any C++ line of code, it's going to be complicated. And even if you take a look at all the other projects, there is none in C++, there is in Rust, and especially Sigma Prime is writing everything in Rust. So I can also leverage the fact that the people with who I'm working are actually developing one of the clients in Rust. So if I need any advice, any help, I can just basically ask them. So the first roadmap that we come was this one. First thing, it was needed for me to understand the context of it. I mean, I was familiar with Ethereum, but not with the current future evolution of it. After that, I was planning to do what we call ETH2 fuzz, so basically coverage-guided fuzzing that will allow us to generate a fuzzing corpora that will be reusable across all the different clients. Then we find out that it could be really interesting to have like a really basic differential fuzzer. That means we will just provide an input and compare the result against all the other implementation, but actually in that case without writing any line of code, because it was just basically you leveraging on all the testing tools available by all the different clients. So that was really easy to implement, and you're going to see that. And the final one, the most painful one in that case, was the differential fuzzer, Beaconfuzz 2. And basically this one is doing structural fuzzing, and especially it's doing differential fuzzing against directly all the clients. And the painful point on that is basically that it was needed to create FFI bandings to basically communicate directly with all those clients written in all those different languages. So that was kind of heavy as a project, but the return on investment, to be honest, was really, really nice, and we're going to see that. So yeah, I mentioned some design choice already. So rewriting everything in Rust, better tooling, and so on and so on. I will not give you too much love about Rust. And after that, why should we create multiple fuzzing tools? And the main reason is we will not target the same piece of code each time. And also, something that is really important to keep in mind is all those different teams are following the same specification over the time. The specification is changing. They are not always following the same one, and they don't always follow the same architecture and reproduce exactly what the specification is all about. So the main idea with creating multiple fuzzing tools is basically to be really fast if there is any broken changes, and if one client is only at the same specification version numbers and another one, and so on, having something modulable that will still allow us to find bugs even if we got some stuff that are broken. After that, the second question we can ask is why not directly use the most efficient technique? As I mentioned, I mean, the big differential fuzzing that, I mean, typically can just find every bug that we're going to find previously. And the main idea is always to find all the long-in fruit the faster. Because if you have, for example, a bug that will you succeed to trigger it, and it's on the SSD decoding part. That means whatever stuff you're going to send that actually trigger this bug, you will get a crash, maybe probably thousands of crashes, and you will just be stuck, and you will not be able to go deeper in the code base and find the bugs that are basically after. So it's really important to be fast on that and try to find all those long-in fruit the faster. So let's talk about the first one, ETH2 fuzz. So as I mentioned, it will be coverage-guided fuzzing. So right now the question is, how are you doing coverage-guided fuzzing on all the language I mentioned? So I will just give you some detail and also show you the result of it. So that will be this specific part, and just keep in mind that everything we are doing, we are not just finding bugs, we are also generating a fuzzing corpora, and that's really interesting and really important, because this corpora will be like a key point into the complete fuzzing ecosystem that we are building right now. So the first one I actually fuzzed was Lighthouse directly, because it was written in Rust, and I was already really familiar with fuzzing with Rust code. And in terms of further available, you have really a bunch of them. Typically, they are just bindings on the C++ fuzzers that already exist, so OffensiveCon, Cargo Fuzz, and AFL. So really easy to use, really easy to maintain. In terms of complexity for the fuzzing harnesses itself, the first step was to basically using those fuzzers generate a SSZ object. So I will just generate some SSZ binary. And after that, I took this SSZ binary, I tried to convert that, so do a decoding into a proper object. Then I tried to load randomly one beacon state, because in that case we have, so there is, when we are doing like processing of this kind of stuff, we have an existing state, and basically the block we're going to process will update this state to another one. So it's always like an association between state and some object to process. So in that case, I've made something really simple. I just took all the unit tests given by the Ethereum Foundation, and I extract all the beacon state, and I basically just pick randomly one each time the fuzzer is restarting or after some time. And finally, the processing of the state transition. So you can see that I mean, in terms of piece of code, it's really simple, not really fancy, but that's also the good part of having all the clients following the same specification. They got the habit to use like the same naming and the same function prototype. So it's even simpler to go through the switching from code base to code base. So the result of that was basically 3 bug founds. So the first one was a memory allocation failure. So it could be weird since we are talking about Rust, and a lot of you might know that Rust is well known to be pretty good in memory safety. But the fact is, this one was basically trying to allocate too much memory, and it was just like growing too fast and at some point just shut down. The two other one was some panics. So panics in Rust are really, really common. There is multiple ways to trigger panics. And if you are developing like a CLI tool, you don't really care of panics. But as a reminder, panics mean denial of service when we are talking about blockchain software. So that's the idea. So the good part of this is that in terms of limitation, I was not really limited when developing the stuff. It was just like taking some more time to just target another part of the code, and that was pretty much all. So that's nice to not be limited either by the fuzzer or either by the client itself. In terms of improvements, there is a lot of them. Basically, the first one will be structural fuzzing using what we call the arbitrary trait. And you're going to see that that's basically what we're going to use later for another tool. And yeah, of course, adding more fuzzing harnesses means increasing the code coverage and potentially finding more bugs. So that was Lighthouse. And if you remember the scheme, this stuff allowed me to generate a fuzzing corpora. So once I have this fuzzing corpora, that will basically be SSZ object, I can just do dump fuzzing. So basically, I'm just taking an existing client. So for this one, it was Prism. And I just use like one of the utility tools they give me, and I just provide everything and hope for crashes. Sadly, I failed to that for this one. I mean, it was not so important to fail at this point because, I mean, basically, it's pretty simple, and that means we have still lots of stuff to do. So this one found no bugs. Okay, whatever. Let's go and do coverage-guided fuzzing again, but this time in Go. So you have multiple Go fuzzer again. So personally, I prefer to use GoFuzz, but with the specific libfuzzer flag that will basically just create an archive, and you can just compile it with Clang, and that's okay. You are basically running libfuzzer and not something else. So that's good. In terms of complexity, I call it medium because the main issue that I got was all the stuff regarding like CGO, and especially they are using some BLS implementation that is like something in C that is used in their project and so on. And on top of that, I was using Bazel. So I don't know if you're familiar with Bazel. It's supposed to help people to maintain and compile more easily their stuff. I mean, it's the case only if you know Bazel. Otherwise, it's a complete mess. So hopefully, they at some point rewrite a bunch of the code they was using, and they call what they say the biggest feature of the year, that is basically having Prism that is Go gettable. So that means really easily installable and usable and so on. So it helped me a lot. So that's basically the snippet of code if you want to fuzz. In that case, it was like a block header. So as you can see, it's taking some bytes. And after that, we are creating some beacon blocks. So, I mean, it was extracted and loaded from somewhere else. We are doing the unmarshal SSZ. So we are doing the decoding of the SSZ object. Once we have the object, we are doing some initialization, and after that, we are doing process block header, and that's okay. You can see that we are using like process block header no verify. That's because, and that's again some really useful feature if you are doing fuzzing. In that case, we ask all the teams to basically provide us like the equivalent of the real function, but without all the mathematical verification and all the cryptographic verification that can be in place. So in that case, there is some BLS verification and so on. And the main goal with that is, since I will do fuzzing, I mean, if there is any hashes comparison and so on, of course it will fail every time, and I will be stuck at this point into the fuzzing process. So basically, I'm just telling them, okay, let's consider that all the verifications that you are doing in terms of cryptography are okay, and for the rest, we can just continue. So the result of that was 3 bugs. So that was nice. in that case, we got some slice bound out of range, one of the most common vulnerability in Go software, and also some nil pointer dereference. Also something really common, especially if you are not checking the error that is returned by the function. So that was the case right there. And yeah, it was nice, it was fine, it was generating some new corpora, some new inputs that was completely actually different for some of them than the Rust one, and so on. So we can just move on that. So after that, again, I took the shot to go to another one, in that case Nimbus, written in Nim. So I will talk a bit more after about Nim. And basically, they are also providing a bunch of testing tools, so dump fuzzing again. And this time, I was a bit more lucky, basically because the implementation and the way they developed the SSD decoding was buggy at this time. So I succeed to find like 5 bugs, and typically that's the kind of low-hanging fruit that you are looking at, because those kind of bugs will have the completely blocking my other coverage guided fuzzer in the future. So that was really nice to just be able to find them. So as you can see, we have some segmentation fault, some assertion error, and index error. So let's discuss quickly about the, what is NIM and why we are getting some segmentation fault. Basically, NIM is a programming language that looks like Python, that you have like some snippet of code right there. And it's a compile language with some strong static typing. But the way it works is basically the NIM compiler will compile your NIM code into C. And after that, they are basically, it's the classical compilation of C program. So you start to see what could go wrong with like NIM to C, C to binary. And of course, we can get some bugs like segmentation fault and so on, but the good part of it is we can easily integrate some and add some existing fuzzer on top of that. And also the good part, in that case, really good part, is that actually the Nimbus team that is developing this stuff is actually like contain a lot of the developer of the NIM programming language. So it was possible just for me to ask them if they can just implement a new fuzzer and basically provide me something really easy to do and just continue my work and find some new bugs. So in terms of complexity, in that case, completely new language to learn and to deal with. Yeah, as I mentioned, the further abstraction was not available, so just need to wait a bit, and it was not like pretty straightforward like the other one. I will try to be quick on the other one, but you get the idea. So this one find 2 bugs, not a lot of limitation, because once I got my libfuzzer running on NIM code, that was pretty nice, and so on. So pretty nice. TQ was in Java. Again, some dump fuzzing, really simple, just using the Docker, getting some CLI clients, testing the stuff. 5 bug found, sorry. So one that was really interesting was the denial of service infinite processing of one basically SSD block, and after that a bunch of exceptions that was not handled directly by the program or by the CLI. In terms of coverage guided fuzzing, it was a bit more messy. Maybe some of you heard about Jazer, that is really famous right now, but at the time it was not available. So basically the only stuff available for me at this time was GQF plus AFL. So I don't know if you ever try it, but it's really slow. I mean, not really useful. So that's why I only found 1 bug with that. It's not because there is no bugs. It's basically because it's taking so much time to fuzz that, I mean, I was just not finding anything else and getting, I don't know, like 1,000 execution per hour or something like that, even less. So as you might know, fuzzing speed is kind of important, and especially when you are dealing with this kind of stuff in that case. So definitely some improvement possible at this time of the project, and it was basically find another way to fuzz Java code. Last one, Lodestar. I'm going to be quick. There is GSFuzz, really useful, really simple to use. That's the harness. I mean, it's difficult to be more simple than that. Basically, you are just launching the stuff. I have not done any dumb fuzzing because just implementing coverage-guided fuzzing in that case was already way, way much simpler. So in that case, 7 bugs found, mainly type error, range error, but either the SSD decoding or either some networking stuff. You can see some ENR string right there. And for example, those ones are basically like the proof of concept to just reproduce the bug. So as you can see, it was not really complicated. So that was nice. So basically, all of that, all this coverage-guided fuzzing leads to this result. So at the end, 26 bugs found so far, 10 of them using just dumb fuzzing, just replaying existing fuzzing corpora, and 16 of them using coverage-guided fuzzing, I mean, generated by the coverage-guided fuzzer. So the pros are pretty simple. I mean, it was really efficient in terms of ratio, like the bugs compared to the time I spent on that for most of them. And the really good part is that coverage-guided fuzzing basically produce reusable and interesting corpora that you can just reuse over time. And it's not just specific for blockchain, to be honest. I mean, you should, whatever the library you are fuzzing, I'm pretty sure there is multiple implementation of it. And I don't know, you are fuzzing, let's say, libpng. So, okay, you are fuzzing libpng, you will generate some PNG picture, but there is not only one parser of libpng. You have some other one written in other language and so on. So if you are fuzzing a project, it can make sense for you to just give it a try and just provide your corpora to other library and see if it's finding any bugs. I mean, the corpora is the key in that case. The good part also was basically what I mentioned, they all follow the same specification, so really easy for me to just switch from one code base to the other. And in terms of unique bugs and so on, as you can see, it was mainly like Lodestar, Nimbus, and TQ that was containing bugs at this time. And you will see that, but it was mainly on SSD decoding stuff. So decoding is hard. So the cons, I mean, in that case, I was mainly dependent of the different coverage-guided fuzzer available for me. So, as I mentioned, for TQ it was a bit hard because basically Java and GQF, AFL, and so on. So it was kind of messy. Also, the cryptographic BLS signature stuff could have been an issue. It had been at the beginning. But after that, as I mentioned, they developed the no verify stuff. Like they allow me to just bypass this part of the stuff, and it was increasing the coverage a lot at this point. Difficult to detect logic bugs, of course, because I'm leveraging on the fact that the coverage-guided fuzzer will basically tell me there is a crash, but I mean, logic bugs most of the time will not lead to a crash. So that's the issue. And finally, time consuming, because I need to write all the fuzzing harness myself and do the testing, running, and so on. So not also the most appealing stuff of the day. So let's right now take a look of basically the other tool I create based on that. So I was working on this stuff, implementing my stuff, and so on and so on. And after some time, I decided that it could be really interesting to basically, as you saw, the dumb fuzzing was basically reusing the different toolings and command line tool available. So I just create like a really basic program in Rust, or I mean, you can even do that in Bash, that will basically take an input, provide that to the different CLI tool, and just take a look at the output, if it's like crashing, not crashing, if it's like parsing properly, getting some error or not, and just comparing the output of all those tools. It was really easy to implement. I mean, I just need to basically compile all the stuff into some Dockers, and after that extract all the command line tool, run them in parallel, and just compare the result. So that stuff was, as I mentioned, really easy, but I only found one bug with it. So the main question could be, is it really useful? Is it really worth it to spend some time for that? And the answer is yes, of course, because what I've done is basically having a way for me to get, for one input, all the output of all the clients. So for debugging later, you will see that it was basically one of the most useful tools for me. Because when you are dealing with logic bugs, it's, in that case, really important to know if the main target you are focusing, is it the one that is buggy, and is it like all the other ones that are doing the stuff right, or is it the opposite? So that's the kind of tooling that in that case makes the more sense. The cons, of course, I mean, it's not a fuzzer. That's basically just like a replayer, a basic command line tool, a script. So I mean, you need to provide some input, and the input are not coming from, they are coming from somewhere. So at some point, you need to have input as well. So that leads me to the biggest part of the project. That was basically the differential fuzzer. So we call it Beaconfuzz v2. And the main idea was to find logic bugs. That's the only goals for us with this piece of software. We are not expecting to get crashes and so on, because if you remember, we already have ETH2Fuzz for that. And I mean, when I was developing the stuff, ETH2Fuzz was still running on some server, and ETH2Diff was only used for like debugging and so on. So if there is any bugs, hopefully, crashing bugs, it was already catched by ETH2Fuzz, or it will be in the future. So it's not really the most important. What was really important in that case was to leverage the fact that we can use structural fuzzing. And the really important part with that is, as I mentioned before that, we was basically generating SSZ object that was then decode and then process. The main idea with structural fuzzing will be to simplify the stuff and only generate valid structure directly at the beginning. So we don't have the SSZ decoding process anymore, and we are only creating some valid structure, valid in the format, maybe not on the content inside, but at least we are generating and simplifying a lot the process. So in terms of complexity, this one was, I would say, medium hard, mainly because it's depending which client you need to deal with, and which language especially. Because we have the structural fuzzing, so for that I've used Rust, I will discuss that right after. And after that you have all the FFI bindings. And the main question is, what is happening if the language is not really like easy to use to create like share libraries that can be used later with FFI bindings. And that was basically what happened. And of course, a lot of manual writing and compilation process. Compilation is the worst in this kind of project. So let's take a look at the architecture of Beaconfuzz. So that's basically what I mentioned. My main goal in that case is to generate attestation, so using structural fuzzing. So in that case, I've used as a main project Lighthouse, because the fuzzer is written in Rust and Lighthouse in Rust as well. And we can leverage on what we call the arbitrary trait. That is a really simple way to basically generate some object using Rust. So really useful, really efficient. So once we get this attestation, I will basically do some SSZ encoding. And the main idea is because when I will communicate with this one, they are written in another language than Rust. And that also means that maybe the memory mapping inside will not be the same. So it's not possible for me to just create an attestation, put that in some chunk of memory, and just tell to the other guy, okay, access to this one, and it will be your structure, and don't worry, it's going to be okay. It's not possible, so what I've done is basically convert that into a SSZ object that is cross-compatible against all the implementation. And after that, I provide that to the different other clients. They have done the decoding, so of course we are waiting a bit of time, but that's okay. And then at this point in time, everyone got the same object following the same specification and containing the exact same data on it. So what I can then do is do all the processing of those objects and do the complete state processing. And after that, at the end, I will just output the result. And the output result could be either the new state of the blockchain, or either it will be just like they got an error, it's not possible, it's like an invalid state or invalid object and so on. So I can detect, in that case, logic bugs at multiple levels. I can detect at this level if they are not able to decode an object that is actually a valid object. I can detect at this point that they are trying to do the processing and they are failing to the processing of this valid object against something else, or, I mean, valid succeed or fail in that case. And the last one is I can check what is the output result and verify that the output result is always the same against all implementation. So we have a really good granularity on that. And of course, the main question is it possible to find bugs with that? And the result is yes. So in that case, we succeed to find 6 bugs, mainly in Prism, and it was really like logic bugs. It was incorrect validation, no verification of some index or subpart of the structure, mainly like one client, so in that case Prism, was maybe validating the state or creating an output state when all the other one was basically rejecting the stuff, and so on and so on. So that was really interesting. And I mean, in terms of results, as I mentioned, all those bugs basically are consensus bugs. That means the kind of one of the most critical for blockchain software. So good result. I mean, the only downside could be maybe the speed, because I mean, there is a lot of SSD encoding, making all the stuff working together. And of course, the most issue is basically that it's taking a long time to write all the bindings, all the stuff, and especially the compilation. You need to compile some share library for all the projects and just run them together and hope it will work. And if one team is basically updating too fast or not using the same specification version, it will always fail because it will always get some different result than the other one. So you also need to be sure they are all following the same specification at the same time. So let me conclude and give you like a big overview of the complete project. That was basically all those tools. So at the end, 33 bugs, almost all critical, as I mentioned. So that's the total number. As you can see, most of them was like Prism, Nimbus, TQ, Lodestar. As you can see, it's only 7, and I've not mentioned anything about Lodestar regarding like differential fuzzing and so on. The main reason of that is at the time I was the Lodestar team was a bit late in terms of developing and following the same versioning of the specification than the other, so it was not useful to add them to the differential fuzzing, but it's not the case anymore. Also, something we have done the community fuzzing. So basically, I put everything into a Docker, and we basically just ask people to run the Docker and try to find bugs for us. And if they succeed, they just report the stuff to the GitHub, and after that we communicate to all the teams, and that's okay. So that was really efficient, and it was really nice to just make my fuzzer run on everyone's laptop. It's only possible if you are dealing with something that is not production ready. In that case, it was under development. If you are familiar with the current evolution, know there is already like a kind of a mainnet for that is running. It will not be something that we will do again right now if it was possible. I mean, it's too impactful if there is any bugs that are just found and not reported directly by us. The main difficulty of this project was basically keeping everything up to date. As I mentioned, specification, team, language, and so on, kind of heavy stuff, and I'm doing fuzzing, so basically I'm trying to find bugs on all the part of the code, and it was painful for the compilation part, I will say. In terms of impacts, that's also really interesting because at the end, we found like 23 crash and panics. And as you can see, we found like 7 logic bugs. So if at some point I was only focused on doing coverage-guided fuzzing, like ETH2Fuzz, I will basically have missed a bunch of bugs that are right there. And most of them, especially the logic one, are definitely critical in that case. So it's really interesting to see that even if it takes the more time, it will lead you to increasing the coverage and find some stuff that will not have been found except in production. And that's the worst cases for us. Lastly, I want to give you a bit of takeaway and statistic, basically, about that. For me, blockchain software are really interesting targets. I mean, you have a bunch of concepts that are really interesting, and you have, as you saw, the networking stack, everything regarding logic that maybe in other kind of software are not as critical and so on. So really interesting, definitely. You don't need to have complex fuzzer to find bugs. I mean, if you remember, I found a bunch of bugs just by doing like replaying the fuzzing corpora, so dumb fuzzing, definitely. And if we take a look at where those bugs was, as you can see, SSD decoding. That was the main source of bugs. Again, decoding is always hard. And in that case, all those bugs was basically just found with dumb fuzzer. So it was already some good state. After that, some networking stuff and some state processing bug as well. Differential fuzzing is really and extremely powerful to find logic bugs. For me, it's the best way you can do it. And I really invite you to take a look at the CryptoFuzz project of Guido. And you will see that it's running on OSSFuzz. And it just found, I think, more than 100 logic bugs in crypto implementation and so on. So it's not a subject that is discussed a lot. And I think it's a bit bad. We start to see some differential fuzzing also, like in browser, especially with like JIT compilation and JIT output. But definitely, I think it will be one of the next few things. If you can try to implement that, and it could be really valuable. For the future of the project, by the time we remove all the GQL, AFL for fuzzing Java code, and we was using Jazer, it's already on production, it's finding bugs, so that's nice. We continue to improve the target and so on, continue to find some bugs. I think we have like 10 or 12 more bugs right now on also the different other phase of Ethereum 2.0, basically. And yeah, we just update also all the fuzzing harnesses, and we actually also just follow the specification. So at some point, the specification right now is using a Snappy, that is another encoding format. And so we are, again, doing some fuzzing on this other part of the code and finding bugs in that as well. The last one, the pie, is basically regarding fuzzing techniques. What was the most efficient? As you can see, coverage guided is a pretty good move, but dumb fuzzing actually performed really well. So don't just think, okay, I'm new to fuzzing, I don't know how to compile and use coverage guided fuzzer and so on. Just give it a try, and even some dumb replayer, and I don't know, I mean, like using dev/dev/urandom can work sometime. Not for that, but it can. And you can already have some good result with that. Thank you.